Picture this. You're standing in what should be the bottom of a lake, but instead you're looking at endless green fields stretching to the horizon. The ground beneath your feet used to be underwater just a few generations ago. Welcome to one of humanity's most audacious engineering projects, the Dutch polder system of the early 1600s, where entire communities decided to literally steal land from the sea itself. Most people think the Dutch just got lucky with their geography. Wrong. The Netherlands in 1600 was basically Europe's version of a sinking ship, except the ship was an entire country, and instead of abandoning it, the Dutch rolled up their sleeves and said, "Hold my beer, we're going to drain this whole thing." About 60% of the Netherlands sits below sea level. That's like trying to build your house in a swimming pool and wondering why you keep getting wet feet. But here's where it gets interesting. These weren't desperate farmers trying to save their flooded fields. The people funding these massive drainage projects were sharp-eyed merchants who saw something everyone else missed: underwater real estate opportunities. They looked at vast lakes and marshes and saw future farmland that could produce grain, support cattle, and generate rental income for centuries. It was like the world's most expensive real estate development project, except instead of clearing trees, they had to move entire bodies of water. The scale of what they attempted would make modern engineers break out in cold sweats. We're talking about draining lakes the size of small cities, moving millions of gallons of water daily, and doing it all with technology that hadn't changed much since medieval times. The biggest challenge wasn't just getting the water out, it was keeping it out forever. Because here's the thing about water, it really, really wants to come back. The story starts with a simple problem that wasn't simple at all. The Dutch lived in what geographers call a delta region, where multiple rivers dump into the sea. Over thousands of years, this created a landscape that was part land, part water, and mostly confusion. Merchants sailing through the area in the late 1500s had to navigate around lakes that appeared and disappeared based on the season, marshes that might or might not support a horse, and rivers that changed course whenever they felt like it. But Dutch merchants weren't known for backing down from a challenge, especially one that smelled like profit. They started forming investment groups called water companies, basically venture capitalists with buckets. These groups would pool their money, hire engineers, and attempt something that sounded completely insane. They would build walls around entire lakes, pump out all the water, and turn the lake bed into farmland. The investors would then rent this brand new land to farmers and collect taxes on the crops. It was like creating your own country, one bucket at a time. The mathematics behind these projects were staggering. A typical polder project in the early 1600s might cost the equivalent of several $1 million in today's money. The Beemster polder, drained between 1607 and 1612, covered over 17,000 acres. That's bigger than Manhattan. The investors were basically betting their fortunes on the idea that Dutch engineering could outsmart physics, economics, and Mother Nature all at the same time. Here's what made these merchants so confident. They'd already seen it work on smaller scales. Dutch engineers had been draining marshes and small lakes for generations, learning through trial and error how to move water where they wanted it to go. But scaling up from draining a farmer's field to draining an entire lake was like going from building a backyard shed to constructing a skyscraper. Same basic principles, completely different level of complexity. The first step in any polder project was something called the survey. And this wasn't your typical property line inspection. Teams of surveyors would spend months mapping every inch of the target area, measuring water depths, testing soil composition, and calculating exactly how much water they'd need to move. They used techniques that wouldn't look out of place in a modern engineering office: triangulation to measure distances, leveling instruments to calculate elevations, and detailed maps showing every bump and hollow in the lake bottom. What they discovered often surprised everyone involved. Lakes that looked uniform from the surface turned out to have complex underwater landscapes, ridges, valleys, and soft spots that would need special attention. Some areas had solid clay foundations perfect for building on, while others were basically underwater quicksand that would swallow anything heavier than a duck. The surveyor's job was to figure out where they could build their water-moving infrastructure and where they'd need to get creative with their engineering solutions. The survey results determined everything about the project's design. Engineers would spread out massive hand-drawn maps, studying the underwater topography like military generals planning a battle. Because in many ways, that's exactly what this was, a battle against water itself. They had to identify the highest and lowest points, plan drainage routes that would work with gravity instead of against it, and figure out where to place the dozens of windmills that would power the whole operation. But the most crucial part of the survey was economic, not engineering. The investors needed to know exactly how much farmland they'd create and how fertile that land would be. Lake bottoms weren't automatically good for farming. Some were rich, dark soil perfect for crops, while others were sandy or peaty ground that might take years to become productive. The difference between good soil and bad soil could make or break the entire financial plan. Once the surveys were complete, the real planning began. Dutch engineers had developed a standardized approach to polder construction that they called the ring Dikes system. Imagine drawing a circle around the area you want to drain, then building a wall along that circle to keep the water out. Simple in concept, but the execution required precision that would impress modern construction crews. The ring dike wasn't just a simple wall. It was an integrated water management system. The dike itself formed the outer boundary, but running along the inside of this wall was the ring canal, a waterway that would collect all the water pumped out of the interior. This canal served multiple purposes. It provided a route for boats to transport materials and crops. It gave the drainage water somewhere to flow, and it created a buffer zone between the farmland and the outside water. Planning the ring canal required some serious hydraulic engineering. The water level in the canal had to be carefully calculated. Too high, and it wouldn't provide enough drainage for the interior fields. Too low, and the pumping systems wouldn't work efficiently. Engineers had to account for seasonal variations, tidal influences, and the capacity of their windmill-powered pumps. It was like designing a bathtub that could empty itself while someone kept trying to fill it back up. The positioning of the windmills along the ring canal was perhaps the most critical design decision. These weren't decorative Dutch windmills from postcards. They were industrial-strength water-moving machines, each one capable of lifting thousands of gallons per hour. Engineers had to calculate the optimal spacing between mills, ensure each one had sufficient wind exposure, and design the canal system so water would flow efficiently from mill to mill. Some polders required multiple stages of pumping. Water from the lowest areas would be lifted to intermediate canals, then lifted again to the ring canal, and finally pumped out to the surrounding rivers or sea. This created a stepped system like a series of water elevators, with windmills at each level working together to move water uphill against gravity. The coordination required was extraordinary. If one mill in the chain broke down, the whole system could back up and flood the farmland they'd worked so hard to create. The maps these engineers produced were works of art as much as technical documents. Hand-drawn with incredible precision, they showed not just the current landscape, but the future one. Fields that didn't exist yet, roads that would be built on drained lake beds, and entire communities that would spring up on land that was still underwater. These maps were selling tools as much as construction plans, used to convince investors that their money would create something permanent and profitable. But the most impressive thing about the planning phase was how the engineers accounted for problems they'd never encountered before. They built redundancy into every system, planned for worst-case scenarios, and designed maintenance procedures for infrastructure that didn't exist yet. They were essentially writing the instruction manual for a technology they were inventing as they went along. The transition from planning to actual construction marked the point where Dutch ambition met Dutch reality, and that reality involved moving more dirt, building more walls, and installing more pumps than anyone had ever attempted before. The construction of a polder started with something that looked deceptively simple: building a wall around a lake. But this wasn't just any wall. It was a structure that had to hold back millions of gallons of water while supporting windmills, roads, and the weight of its own massive bulk. The foundation of every ring dike started with fascine mats, basically enormous underwater carpets made from bundled brushwood. Picture trying to weave a basket the size of a football field, except you're doing it underwater, and the basket has to support a wall that's taller than a house. Teams of workers would gather willow branches, birch twigs, and whatever flexible wood they could find, then weave them into mats that could be 30 feet wide and hundreds of feet long. Getting these fascine mats into position required coordination that would make a military operation look simple. The mats had to be sunk in exactly the right spots, weighted down with stones, and layered in specific patterns to create a stable foundation. Workers standing in boats would use long poles to guide the mats into place, while others dove underwater to secure them with rocks and stakes. It was like trying to lay carpet while swimming, except the carpet weighed several tons, and your living room was the bottom of a lake. On top of these fascine foundations, workers built the actual dike using whatever materials they could find locally. Clay was the premium choice. It packed well, resisted water, and created a solid barrier that could last for centuries. But clay wasn't always available, so engineers got creative with alternatives. Sand mixed with organic matter, layers of different soil types, and even controlled amounts of peat all became part of the dike construction recipe. The cross-section of a properly built ring dike was like a layer cake designed by someone obsessed with water resistance. The core was usually clay or other impermeable material, surrounded by layers of sand and gravel that provided drainage and structural support. The outer face, the side that would face the water, got special treatment with sod revetments, basically a living carpet of grass and roots that would protect the dike from wave action and erosion. Building these dikes required an army of workers doing jobs that ranged from skilled to backbreaking. Specialized craftsmen called dike reeves supervised the construction, ensuring that each section met the exacting standards necessary to hold back the water. Regular laborers hauled materials, packed clay, and did the heavy lifting that turned engineering drawings into physical barriers. And then there were the pile drivers, workers who used massive wooden hammers to drive support posts into soft spots where the regular dike construction wouldn't hold. The pile driving operation was perhaps the most dramatic part of dike construction. When surveyors identified areas where the lake bottom was too soft to support a conventional dike, workers would drive wooden piles deep into the mud until they hit solid ground. These piles, often made from entire tree trunks, would be hammered into place using devices that looked like medieval siege weapons. The sound of pile driving could be heard for miles, a rhythmic pounding that announced to everyone within earshot that the Dutch were once again attempting to rearrange geography. But the real engineering challenges came when builders reached the spots where their ring dike had to connect with existing waterways. They couldn't just build a solid wall and call it done. They needed gates and sluices that could control water flow while maintaining the integrity of the dike system. These sluice gates were marvels of hydraulic engineering, designed to let water out during low tide while preventing it from rushing back in when the tide rose. Each sluice gate was essentially a one-way valve the size of a small building. Heavy wooden doors hung on massive hinges, designed to swing open when water pressure pushed from inside the polder and slam shut when outside water tried to flow back in. The timing had to be perfect. Open the sluices too early, and outside water would rush in. Wait too long, and the water inside the polder would have nowhere to go and would back up into the newly drained fields. The construction of these sluice gates required precision that would make modern engineers nervous. Workers had to build watertight chambers in the middle of active waterways, essentially constructing buildings underwater, while the tide tried to wash away their work twice a day. The gates themselves were massive wooden structures reinforced with iron, hung on hinges that had to support thousands of pounds while operating smoothly enough to respond to subtle changes in water pressure. But here's where Dutch engineering got really clever. They designed these sluices to be self-operating. The gates would open and close automatically based on water levels, without requiring someone to stand there turning cranks all day. When the water inside the polder rose higher than the outside level, the pressure difference would push the gates open. When the tide came in and reversed that pressure, the gates would slam shut like enormous one-way valves. It was mechanical automation centuries before anyone invented computers. The most dangerous part of sluice construction happened during what workers called the final closure, the moment when they sealed the last gap in the ring dike and officially separated the interior water from the outside world. Up until this point, water could still flow freely in and out of the construction area. But once that final section of dike was completed, everything inside became a closed system dependent entirely on the pumping infrastructure they'd built. The closure operation required split-second timing and nerves of steel. Workers would prepare massive bundles of fascine mats, position them near the final gap, then drop everything into place during a single low-tide cycle. They had maybe 6 hours to seal a gap that might be hundreds of feet wide, and if they didn't finish before the tide returned, the rushing water could wash away weeks of work and potentially drown anyone caught in the gap. Once the ring dike was complete and the sluices were operational, the real magic of Dutch engineering kicked into high gear. The windmill system, what the Dutch called bemaling, was like nothing anyone had ever attempted before. We're not talking about a single windmill grinding grain in a village. This was an industrial-scale water-moving operation that required dozens of mills working in perfect coordination, operating 24 hours a day, pumping millions of gallons of water uphill against gravity. The star of this operation was the polder mill, and these weren't your typical picturesque windmills with 4 arms turning lazily in the breeze. These were purpose-built water-moving machines, equipped with massive scoop wheels that could lift tremendous volumes of water with each rotation. Picture a water wheel running in reverse. Instead of water turning the wheel was lifting water from a lower level to a higher one. The scoop wheels themselves were engineering marvels that would impress modern pump manufacturers. Made from wood and iron, they could be 20 feet in diameter or larger, with dozens of individual scoops around the circumference. As the windmill's arms caught the wind and turned the gearing system, these massive wheels would rotate in their channels, each scoop lifting gallons of water with every revolution. The sound was apparently unforgettable, a constant whooshing and splashing that announced to everyone within miles that the battle against water was in full swing. But getting the power from the windmill's arms to the scoop wheel required some serious mechanical engineering. The mills used complex gear systems that would make a clockmaker jealous, wooden cogs and iron wheels that had to transfer power efficiently while dealing with the constant stress of moving water uphill. The gear ratios had to be calculated precisely to match the wind speed with the pumping capacity, and everything had to be built strong enough to operate continuously for years without major repairs. The millwrights who built and maintained these systems were like the rocket scientists of their day. They understood wind patterns, water flow, mechanical advantage, and structural engineering all rolled into one profession. A good millwright could listen to the sound of a mill and tell you exactly what needed adjustment, repair, or replacement. They could predict when the wind would be strong enough for optimal pumping and when the mills needed to be shut down to prevent damage during storms. Maintenance of the mill system was a never-ending job that required constant attention. The wooden gears wore down from the constant grinding, the scoop wheels needed regular cleaning to remove debris, and the mill arms had to be adjusted seasonally to account for changing wind patterns. Some mills employed full-time operators whose only job was to monitor the equipment and make minor adjustments throughout the day. It was like having a full-time mechanic for every piece of heavy machinery, except the machinery was powered by something you couldn't control, the wind. The coordination between multiple mills, was perhaps the most impressive aspect of the whole system. In a large polder, you might have 30 or 40 mills working together, each one responsible for draining a specific section of the interior. The water from lower-level mills would flow into intermediate canals, where higher-level mills would pick it up and lift it further toward the ring canal. If one mill in this chain broke down or couldn't keep up, the whole system could back up like a clogged drain, potentially flooding areas that had been dry for months. The ring canal itself was the highway that made the whole system work. This wasn't just a ditch running around the perimeter. It was a carefully engineered waterway with specific depths, slopes, and flow characteristics designed to move water efficiently toward the exit points. The canal had to be deep enough to handle the output from all the interior mills, wide enough to accommodate the boats that would transport materials and crops, and properly graded so water would flow toward the sluice gates without creating stagnant areas. Managing the water flow in the ring canal required understanding tidal timing that would challenge modern harbour masters. The goal was to move accumulated water out of the system during low tide, when the outside water level was lowest and the sluice gates could operate most efficiently. This meant coordinating the pumping schedule of dozens of mills with the twice-daily tide cycle, ensuring maximum output when the gates could actually release water to the outside. Winter operations presented special challenges that tested every aspect of the system. Ice formation could jam the scoop wheels, freeze the sluice gates shut, and create blockages in the ring canal that brought the whole drainage operation to a halt. Some mills were equipped with special ice-breaking attachments, while others had to be shut down entirely during the coldest months. The accumulated water during these shutdowns would freeze into temporary lakes inside the polder, creating a spring flood risk when the ice melted faster than the mills could handle the runoff. Lockkeepers became crucial personnel in the operation, responsible for monitoring water levels, operating manual controls when the automatic systems couldn't handle unusual conditions, and coordinating between different sections of the drainage network. These weren't just guys who opened and closed gates. They were hydraulic engineers who understood the entire system and could make split-second decisions that prevented floods or equipment damage. The most nerve-wracking part of the whole operation was the constant awareness that failure meant disaster. Unlike most engineering projects, where a breakdown means inconvenience or expense, a failure in the polder system meant that thousands of acres of farmland and entire communities could disappear underwater in a matter of hours. The water was always there, always pressing against the dikes, always ready to reclaim the land that humans had stolen from it. But when everything worked correctly, the transformation was nothing short of miraculous. Areas that had been underwater for centuries gradually emerged as the mill system lowered the water level foot by foot, day by day. First, the highest ridges would appear like islands in a shrinking sea. Then larger areas would emerge, revealing lake bottoms that hadn't seen sunlight in generations. Finally, the entire interior would be exposed, creating thousands of acres of new land ready for the next phase of the operation, turning a drained lake bed into productive farmland. The moment when the last of the water disappeared from the interior marked just the beginning of an entirely new challenge. What the Dutch discovered was that draining a lake was like unwrapping a present you weren't sure you wanted. Sometimes what you found underneath was exactly what you hoped for, and sometimes it was a soggy mess that would take years to become useful. The newly exposed lakebed looked like the surface of an alien planet. Centuries of underwater sediment had created a landscape that was part mud, part organic matter, and entirely unfamiliar to anyone who'd only seen it from above. The soil was saturated with so much water that walking on it was like trying to hike across a giant sponge. Workers would sink knee-deep into what looked like solid ground, and horses had to be equipped with special wide shoes to prevent them from disappearing entirely into the muck. But this soggy beginning was exactly what Dutch engineers had planned for. They understood that turning a lake bottom into farmland was a process that couldn't be rushed no matter how eager the investors were to start collecting rent. The first step was creating a drainage grid inside the polder, a network of ditches that would carry water from every field to the ring canal system. Cutting these interior ditches was backbreaking work that required workers to essentially sculpt the landscape by hand. Teams would mark out straight lines across the muddy expanse, then dig channels that followed precise gradients calculated to ensure water would flow toward the pumping stations. The ditches had to be deep enough to drain the surrounding fields, but not so deep that they destabilized the soft soil. It was like performing surgery on the earth itself, except the patient was made of mud and kept trying to heal itself by filling back in. The grid pattern that emerged from this ditch-cutting operation was a masterpiece of practical geometry. Fields were laid out in long, narrow strips that maximized drainage while minimizing the amount of ditch construction required. Roads followed the tops of the drainage ditches, creating elevated pathways that would remain passable even during wet seasons. Bridges appeared wherever roads crossed waterways, each one a small engineering project that had to account for boat traffic, water flow, and the constant settling of the underlying soil. The soil settling issue was something that caught many investors by surprise, even though experienced engineers had warned them about it. As the newly drained land dried out, the organic matter in the soil would compress and oxidize, causing the entire surface to sink. A field that started at sea level might drop several feet over the first decade, requiring constant adjustments to the drainage system and ongoing modifications to buildings and infrastructure. Peat oxidation was the most dramatic part of this settling process. Areas with high concentrations of organic matter would literally shrink as the peat dried out and decomposed in contact with air for the first time in centuries. Some sections of newly drained polders would develop a landscape that looked like a moonscape, with ridges and depressions appearing seemingly overnight as different soil types settled at different rates. Managing this subsidence became a full-time job that required constant monitoring and adjustment. Water boards employed teams of surveyors whose only job was measuring elevation changes and recommending modifications to the drainage network. Ditches that had been perfectly graded when first dug might need to be deepened or rerouted as the surrounding land settled. Buildings had to be constructed on deep foundations that could handle several feet of soil movement without cracking or tilting. But the most challenging aspect of turning drained lakebed into productive farmland was dealing with the salt. Centuries of tidal influence had left the soil saturated with salt water, and crops wouldn't grow in earth that was essentially a giant pickle. The solution was a process called desalinization that involved flooding the fields with fresh water repeatedly, then draining it away to carry the salt with it. This desalinization process could take several years and required enormous amounts of fresh water. Water that had to be pumped in from outside rivers using the same windmill system that was simultaneously pumping salt water out. It was like trying to rinse out a sponge, while the sponge was the size of several city blocks. Some polders went through this cycle dozens of times before the soil became suitable for growing crops. The first farmers who moved onto newly drained polder land were taking a huge gamble on soil that nobody really understood yet. These pioneer farmers had to experiment with crops that could tolerate unusual soil conditions, drainage patterns that were still being adjusted, and weather patterns that might be different from the surrounding area. Some became wealthy by figuring out what grew well in the unique conditions. Others went bankrupt trying to force traditional farming methods onto land that wasn't ready for them. The parceling of fields into individual farm plots was itself a complex operation that had to balance practical farming needs with the geometric requirements of the drainage system. Fields couldn't just be laid out in convenient squares. They had to follow the drainage grid, account for soil quality variations, and provide access to the transportation network. Land surveyors would spend months mapping out boundaries that would determine property lines for centuries to come. The people who made all this possible formed a complex social and economic network that was unlike anything else in Europe at the time. At the top were the investors, wealthy merchants and nobles who had put up the initial capital for the project. These weren't just passive investors waiting for returns. They were actively involved in decision-making about everything from mill maintenance to crop selection. Some even moved to the newly created land to oversee their investments personally. The water boards, called Hughimrat Shap, became the governing bodies that managed the day-to-day operations of each polder. These weren't government agencies in the traditional sense. They were cooperative organizations funded by the landowners and farmers who depended on the drainage system. The water boards had their own taxes, their own courts, and their own enforcement mechanisms. They could fine farmers who didn't maintain their ditches properly, order emergency repairs during flood threats, and even seize property from landowners who didn't pay their water management fees. The inspections conducted by water board officials known as SCU were serious affairs that could make or break individual farmers. Teams of inspectors would examine every ditch, every bridge, and every section of dike to ensure that maintenance standards were being met. A farmer whose ditches were too shallow or whose bridge was blocking water flow could face fines that would bankrupt them. But these inspections weren't arbitrary. They were based on the understanding that one person's poor maintenance could flood their neighbours' crops and undermine the entire system. The millers who operated the windmill pumps became some of the most important and well-paid workers in the polder communities. A skilled miller could mean the difference between successful drainage and catastrophic flooding, so these workers commanded salaries that rivaled those of master craftsmen in the cities. Miller families often worked the same mills for generations, passing down knowledge about wind patterns, mechanical maintenance, and emergency procedures that couldn't be learned from books. Dike reeves held positions that combined engineering expertise with legal authority. They had the power to order emergency repairs, conscript labour during flood threats, and make life or death decisions about water management during storms. Some dike reeves became legendary figures in their communities, remembered for decades for their quick thinking during crisis situations, or their innovative solutions to drainage problems. The financial complexity of running a polder rivaled that of managing a small city. Land leases had to account for soil quality variations, drainage costs, and the ongoing risk of flooding. Assessments were calculated based on acreage, crop yields, and the benefits each property received from the water management system. The accounting records from successful polders reveal sophisticated financial management that tracked everything from windmill maintenance costs to the wages of ditch diggers. But all this careful planning and management couldn't eliminate the constant threat of natural disasters. Storm surges remained the nightmare scenario that kept every polder manager awake at night during bad weather. When North Sea storms combined with high tides and strong winds, the water level outside the ring dikes could rise faster than the interior pumping system could handle. The pressure on the dike walls during these events was enormous, and even small leaks could quickly expand into catastrophic breaches. Emergency response procedures during storm threats involved the entire community in a coordinated effort that resembled military mobilization. Everyone had assigned roles. Some would reinforce vulnerable sections of the dikes with sandbags and extra fascine mats. Others would operate emergency pumps, and still others would evacuate livestock and valuable equipment to higher ground. The sound of storm bells could bring hundreds of people running to predetermined positions within minutes. The most dramatic emergency repairs involved something called emergency brush mat closures. When a section of dike began to fail during a storm, workers would attempt to seal the breach by sinking massive bundles of weighted brushwood directly into the gap. This was incredibly dangerous work that had to be done while storm waves were crashing over the dike and flooding was actively occurring. Workers would essentially throw themselves into the breach with armloads of brush, trying to plug the hole before it widened beyond repair. Mill breakdowns during storms created cascading failures that could doom an entire polder. If key pumps failed when they were most needed, water would back up through the entire drainage network, potentially flooding areas that had been dry for decades. Emergency repair crews would work on broken mills during storms, replacing broken gears and clearing jammed scoop wheels, while wind and rain made every task exponentially more difficult. The flood drills conducted by waterboards were elaborate exercises that tested every aspect of the emergency response system. These weren't simple evacuations. They were complex operations that practiced coordination between multiple mills, communication systems that could function during storms, and repair procedures that might need to be executed in complete darkness. Some communities held annual flood drills that became social events, with competitions between different work teams and celebrations afterward for successful completion. But when everything worked correctly and the storms passed without major damage, polder communities would return to the routine that defined their existence, the constant, never-ending maintenance that kept their artificial landscape functioning. This wasn't the kind of farming where you planted crops in spring and harvested them in fall. Polder agriculture was a year-round battle against water, soil chemistry, and the gradual subsidence that threatened to drag everything back underwater. The first successful harvests from newly drained polder land were celebrations that marked the transformation of investment and engineering into actual wealth. Grain fields that produced crops where fish had swum just a few years earlier represented the ultimate victory of human ingenuity over natural obstacles. But these celebrations also marked the beginning of an obligation that would last forever: the commitment to maintaining the complex systems that made the land possible. From the moment the first seeds sprouted in polder soil, the countdown began on a maintenance schedule that could never be ignored. Mills needed daily attention, ditches required annual cleaning, dikes demanded constant monitoring, and the pumping system had to operate reliably every single day for the rest of time. A polder wasn't just a piece of land, it was a machine that happened to grow crops, and like any machine, it would break down catastrophically if maintenance was deferred. The success of the Dutch polder system created a model that spread far beyond the Netherlands, inspiring similar projects across Europe and eventually around the world. But more importantly, it demonstrated that large-scale environmental engineering was possible when you combined technical expertise with cooperative governance and long-term financial commitment. The polders proved that humans could literally create new geography when they were willing to work together and think beyond the limitations of their current situation. The wealth that flowed from these drained lands helped fuel the Dutch Golden Age, providing the agricultural surplus that supported urban growth and international trade. Polder-grown grain fed the cities, polder dairy products became export commodities, and the rental income from polder farms funded further expansion of the Dutch maritime empire. The land stolen from the sea became the foundation for a prosperity that lasted for centuries. Today, driving through the Dutch countryside, you're traveling through one of humanity's greatest engineering achievements, a landscape that exists only because previous generations refused to accept the limitations that nature had imposed on them. Those endless flat fields, perfectly straight canals, and geometric road patterns aren't natural features. They're the visible evidence of a time when people looked at impossible problems and decided to solve them anyway, one bucket of water at a time. The Dutch polder system stands as proof that the most audacious engineering projects succeed not just because of technical brilliance, but because of the social systems that support them. The combination of engineering innovation and cooperative governance that made the polders possible created a model for large-scale environmental management that remains relevant today. In an age when we face our own seemingly impossible environmental challenges, the story of how the Dutch tamed the sea offers both inspiration and practical lessons about what humans can accomplish when they commit to working together on solutions that will benefit not just themselves, but generations yet to come.